In this video, we're going to talk about cofactor expansion. This will make calculating determinants a lot easier. So, given a matrix A, which is A11, all the way down to A and N, again, these matrices have to be square, we say the ij cofactor expansion of A, we're going to write as capital C with subscripts ij, where Cij is equal to -1 to the I plus j times the determinant of capital Aij. So how is this different than just Aij, or in fact the original expression? Well, now we're able to write the determinant of A as A11C11 plus A12C12 plus all the way up to A1n C1n. So no longer do we have to write the determinant of A11 and then subtract and add and subtract every other term. So the point here is that using the C11, we can just plug our row and column into the formula to figure out if we have to add or subtract. Also, now we don't have to do it exactly across the first row. So this example here is the cofactor expansion across the first row. And it's across the first row because our first entries are all going to be in the first row. So it goes from 1, 1 all the way up to 1n. The nice thing is that we can do this around the ith column or across the jth row. We can do this forever. So why can we do this? Well, before, if we did this, we'd have to count. We'd have to say, okay, this one's plus, this one's minus, this one's plus, this one's minus, this one's plus, so on and so forth. However, with our formula, so remember we have -1 to the I plus j, well, now we can say, okay, what is the A46 entry going to be? Is it going to be positive or negative? Well, it's going to be -1 to the 4 plus 6, which is -1 to the 10. So this entry here, A46, is going to be positive. So that's what we can do with this. So now we can do cofactor expansion to find the determinant along the ith row. So we hold the ith row constant here, or we across the jth row. So we'll hold the jth row constant. So now we can do cofactor expansion wherever we want. So when is this useful? Well, let's use cofactor expansion to find the determinant of this matrix. So what's good about this is now we use zeros to our advantage. So I see a 0 in the A11 column. So what I'm going to do is I'm going to do cofactor expansions across the first row. So are 0, 5, 1, 4, -3, 0, 2, 4, 1. Okay, so let's write this out formally. This is going to be A11 C11 plus A12 C12 plus A1C C13. Okay, so what is A11? It's 0, so C11 doesn't matter. A12 is going to be 5. Okay, so what's C12? Well, remember, it's -1 to the power of I plus j, so that's going to be -1 to the 1 plus 2. And then we have to multiply that by the determinant of the submatrix A12. So in this case, A12 means we take out the first column, or the first row and the second column. So we're going to be left with 4, 0, 2, 1. And then finally, we're going to add A13. A13 is just 1. C13 is going to be -1 to the power of 1 plus 3. And then we'll multiply this by the submatrix A13. So that's not the first row, not the third column. So we're left with 4, -3, 2, and 4. Okay, so this is going to be 0 for the first term. 5 times -1 to the power of 3, it's going to be -5. The determinant of 4021 is going to be 4 times 1 minus 2 times 0. Then we're going to add, well, -1 to the power of 4 is 1. So we're just going to end up adding the determinant of 4, -3, 2, 4. So it's going to be 4 times 4 is 16, minus 2 times 3, that's -6. So we're going to subtract -6, which is the same as adding 6. So here we get -20 plus 22. So our determinant is going to be equal to -2. So another note here, I said before that determinants can be really big. they can also be negative, so that's okay. But because, again, this is not 0, we know that this matrix is going to be invertible. So again, another point that I made last time is if the determinant is not equal to 0, then the matrix is invertible. So these are just side points I'll bring up to remind you every once in a while. Okay, so that's nice. We eliminated 1, 0, but we can do so much better. So look at this matrix here. 6005. This is really good. This is a great line. It has 2 zeros in it. And we have 1, 7, 2, negative 5, but here we have 2, 0, 0, 0. Let's do cofactor expansion across this third row here. So, okay, this is going to be we'll call this A31 times C31 plus A32 times C32 plus A33 times C33 plus A34 times C34. So that's cofactor expansion across the third row. Okay, C31, this is going to be 2. And then we have to multiply this by the determinant of the submatrix of A31. So in this case here, we get rid of the third row and the first column. So now we're left with the determinant of 0, 0, 5, 7, 2, negative 5, and 3, 1, 8. And then, of course, I also have to take negative 1 to the power of I plus j, which will be 3 plus 1. Okay, so that's A31, C31. Now we need to do the next one. Okay, A32 is 0, so that's done. A33 is 0. A34 is 0, so those will all be 0. And look, now with one operation and one calculation, we have reduced this to 2 times the determinant of 0, 0, 5, 7, 2, negative 5, 3, 1, 8. But it gets even better, because now we have another row we can do this with. We have 0, 0, 5. So this is going to be 2 times A11, A11, or I guess A11, C11, plus A12, C12, plus A13, C13. But at this point, well, A11 is 0, A12 is 0, so all we have to do is A13, C13. That's going to be 5 times, well, negative 1 to the I plus j, so it's 1 plus 3. And then the determinant, taking out the first row in the third column, so we're going to be left with 7, 2, 3, 1. All right. So now at this point, this is going to be 2 times 0, 0 plus 5 times negative 1 to the 4. That's 5 times the determinant of 7, 2, 3, 1, which is going to be 7 times 1 minus 3 times 2. That's 6. So our determinant is going to be 10. So with cofactor expansion, we made this a lot easier, because before we would have had to go across the top first. So we would have had to do 6 times this submatrix, and then minus plus minus 5 times this submatrix, and then we would have had to do the determinant of 2 of these submatrices independently, and we would have had to move across the top row here. So we never would have been able to simplify our work, and doing this by hand would have taken a lot longer. So on exams, cofactor expansion is your best friend. Pick the easiest lines and do it. Okay, so one last theorem. If A is triangular, then the determinant of A is the product of diagonal lines, or diagonal entries. So if I take a look at the determinant of this is just going to be equal to 3 times 4 times 2, because these are the diagonal entries. Now, why is this the case? Well, we could do this generally. So if you want to make a proof of a general example, you can, but I'm going to do this with this example. So first we can do cofactor expansion down the first column. So this is going to be A11, C11 plus A21, C21 plus A31, C31. So these A21s and A31s, these are going to be equal to 0. So we really just have to look at A11, C11. And this is just going to be 3 times -1 to the 1 plus 1 times the determinant of 4, 5, 0, 2. So this is just equal to 3 times the determinant of 4, 5, 0, 2. And again, what's the determinant of 4, 5, 0, 2? Well, this is just going to be 4 times 2 minus 5 times 0. So this is equal to 3 times 4 times 2. So this was not a full proof of this. This was just an example that shows the proof to be true. But if you wanted to do this, you would start with induction on something like A11, A12, A21, A22. So this would be 0, of course. So you can do induction with this. So you'd show the base case. And then what you do is you'd assume for a smaller matrix that, say, A22 all the way down to A and N is true. And then you could add a new row, A11, that goes all the way up to A1N, all the way down to A1, AN1. And then you could show the determinant is true here as well. So again, these would all be zeros here. So what would happen is you'd say, okay, the determinant of this is equal to the diagonal entries. Then we added this new row here, but these are all zeros. So if we do cofactor expansion, it's just going to be this times the determinant of the diagonals. So it does generalize very simply into an inductive proof, but I think visually is enough to kind of grasp that. But if you want it done, please leave it in the comments below and I will do it. So if you have any questions, leave them down there and I will answer them the best that I can.